So good morning. Welcome to Mass 802, Algebraic Topology. So in the last class, we look at the concept of homotopy. We define homotopy and homotopy equivalence. We also talk about deformation retraction. Today we are going to look at, part of what we did was to show that the space, a disk. Remember, as part of the example yesterday, we look at a disk and we show that it's homotopic to is a point. Spaces that are homotopic to a point are called contractible. Like the Euclidean space, the entire space, you can show that it is homotopic to a point. Such spaces are called contractible. But today we are going to look at path homotopy. So this will be section 2.2. It's a path homotopy. So I will start by reminding you what a path is. So definition, a path in a space. And I always say, when we say a space X here, we mean a topological space. It's a continuous map. F from I into X. So any continuous mapping from I, you remember I is the closed bounded interval, 0, 1. So any such continuous mapping from I into the space is called a path. Imagine you have your space here, can be of any sort, but then the interval is 0, 1, closed bounded interval. So any mapping that sends the entire interval into the space, the image of that map is can be thought of as a path in the space. So here will be the image of 0, and this will be the image of the point 1. So that is a path. Okay? Because this space the domain is a closed and bounded set. So therefore, over there, it must also be closed and bounded because the mapping is continuous. So that is the only requirement, that the map should be continuous and the domain of the mapping should be 1-to-1, should be the interval 0, 1. Okay? And then we say it is a path from this point to that point. Okay? The point f of 0 and f of 1 are called the end points of the path. So of f, the path itself. Okay? So that is what we mean by a path. So what we did yesterday was to look at two functions, continuous maps, from a topological space to another topological space, and then we say these ones are F and G are homotopic if there is a family, a continuous family of continuous mapping, so that the first member of the family is F and the last member is G, and this family is indexed by T coming from the interval 0, 1. And then we say they are homotopic. But then path homotopy differ a little bit in the sense that to define the homotopy of path, it has to be relative to the endpoint. So it's actually the homotopy we defined in the last lecture, but relative to the endpoint. Okay? So two paths. um, F and G. So, well, paths are continuous mapping, as we have just said, are called, so, but we want, are called homotopic, path homotopic. If they are homotopic, relative to their endpoint. So relative to their endpoint, which means there should be a homotopy from F to G, and throughout the homotopy, the initial point and the terminal point of the path must be the same. And this condition is already imposing an extra restriction that the initial point, so the path must share the initial point, meaning f of 0 must be equal to g of 0, and f of 1 must be equal to g of 1. Because the first member of the homotopy must be f, and the last member must be what? G. And if we say the homotopy should be relative to the endpoint, so if this is the endpoint, this one is x0, and this is x1, then we are saying, given the homotopy, so that is, if they are path homotopic, if there is a homotopy, what do we define to be a homotopy? A family of continuous family of maps. So FT, and these maps should be from where to where? From the domain into X. So there should be continuous family of paths, because these are continuous mapping. So if there is a homotopy consisting of paths like this, T from the interval, such that so homotopy relative to the endpoint, meaning what? Two conditions. Okay. Well, first of all, f0 should be equal to f, because it should be a homotopy from f to g. Okay. And then the second condition is to say that f1 should be equal to g. I hope it's okay. And then the third condition is to say that ft of s, so if I take my argument from the domain here to be s, this should be equal to, so ft of s or ft of 0 should be equal to x naught. That is number 3. And number 4, ft of 1 should also be equal to x1 for all t. This should happen for all t in the interval, for all t in the interval, in the index interval. Then this is the homotopy. I hope it's okay. So throughout the homotopy, well, at time t equal to 0, the first member of the family of the homotopy should be F, should be the mapping F. That should be F0. And then the last member should be the map G. So F1 should be G. And then the remaining members can be, so F half should be somewhere around here, F half. And then you have F, many other ones. So it's like you are continuously deforming this path until it takes the shape of G, until it is the path G. So you are deforming it in this direction like this. F0, F half up to F1. But then F0 should be F and F1 should be equal to G. And the homotopy should be in the sense that throughout the homotopy for each F, 0 is mapped to X0. So the initial point of the path, all of them, should be equal to X0. And then the terminal point of all the paths should also be equal to X1. So they must share the same end and terminal point, all members of the family. And then F and G inclusive. I hope it's okay. It's okay, Ko? All right. So this is what we call path homotopic. So two paths are homotopic if they are homotopic relative to their endpoints. I hope it's okay. You remember yesterday we talked about function being homotopic. And then we say if there is a subset of the space such that throughout the homotopy, the space X, you remember how we define it? We say F, X, two functions F and G are homotopic to Y, okay? If there is a family of maps Ft from X to Y such that, F0 is F and F1 is G, and that if it happened that there is a subset A of X, A is a subset of X such that Ft restricted to A is independent of A. Are you following? So you see the point 0 and the point 1 here will constitute of our set A. So that throughout the homotopy, the image of 0 and the image of 1 are independent of the time t. Always they are being mapped to x0 or x0 and x1. I hope it's okay. So the mapping restricted to this endpoint is independent of the time. I hope it's okay. Then you now say it's homotopic relative to the endpoints. Relative to the endpoint, relative to 0 and 1. I hope it's okay. So this is when we say two paths are homotopic. So we can show that for example, we can easily show that example that in R, in Rn, the Euclidean space, any two paths F and G with, so what is a path? It's a continuous mapping from the interval 0, 1 into the space. I hope it's okay. With F sharing the same, so F0 equal to G0 and F1 equal to G1, sharing the same endpoint are path homotopic. And this is true because you can always define that homotopy. So we can choose the homotopy So we should define a homotopy that satisfies these properties relative to what? So choose this homotopy, Ft, given by, so Ft of S is equal to 1 minus T into F of S plus T into G of S. Yeah. This homotopy, this will be a homotopy relative to the endpoints, relative to 0 and 1. We will satisfy the 4 properties over there. You can see that, you can easily see that it has the properties. So this is a homotopy. Clearly this mapping, one thing you should check is that it is a continuous map, because this is a linear combination of 2 continuous maps. You know, if the scalar product of continuous maps is also continuous, and then when you add 2 continuous maps in this way, you get a continuous map. So this is a linear combination of 2 continuous mappings, so it is a continuous map for every t. So it's a family of continuous map, continuous family, in the sense that the associated map is continuous, as we said in the last class. So, but here, to check that this homotopy starts from F and ends at G, so it is a homotopy from F to G. You can quickly see that F0 of S is equal to what? So it will be F of S. That is the first condition. And the second condition is that F1 of S is equal to what? G of S. That is the second condition. The third condition is that the homotopy should be relative to 0 and 1. So you check what happened at 0. F of 0 should be equal to what? Well, it will be 1 minus T F of 0. So 1 minus T F of 0 plus T G of what? 0. Is that okay? But that is will be, that will be what? It will be F of 0. But then, you know, F of 0 and G of 0 are the same. So this will cancel, because this equality is happening. So if I say this is x naught, so what we have is x naught. I hope it's okay. And if I call this endpoint x1, the other one should give us also x1. So f of t, ft of 1 should be equal to, so what do we have there? We have what? We should get x1. So it will be 1 minus t f1 plus t f1. Well, this is just like redoing the other one. So this is still f of 1, which is f of g, and that is x1. Okay? So for all t, you always get x1 for the 0. So the homotopy is independent of 0 and 1, the end points. So therefore, this is a homotopy connecting f and g, and it is relative to the end points they are sharing. So in Rn, if you take any 2 points, any 2 paths sharing the same ends, they are always homotopic. Okay? They are always what? Homotopic. In fact, we can generalize this example to the fact that any 2 paths in a convex subset of Rn are homotopic. So convex subset X of Rn path homotopic. In fact, in general, if it is a convex subset, it means the line joining any 2 points sits completely inside the space. I hope it's okay. That is when we say a space is convex. So, and that line joining is the linear combination. I hope it's okay. So if the space is convex, this linear combination for every t will always be sitting inside. So the homotopy is always happening inside the space. With this linear, this is called the linear homotopy. That is linear parameterization. So it's like you are reparameterizing linearly. So this is called, this linear combination will always be in the space if the space is convex. So in general, for any convex subset of a Euclidean space, any two paths will always be homotopic. Like which space? Like a disk. You know, if you are in a disk like this, and then you describe path in the disk. If you have a path and another path, then the two are always, F and G are always homotopic, because you can always draw this straight line to get from F to G without exiting the space. You are always inside the space because it is convex. But this space, this one, an annulus, is not convex. Okay? So if you have a path like this, F, and another path like this, G, the line joining point from this path to that path, the straight line joining the path will not sit at this place, is you are already outside so it's not a convex subset of the set of real numbers of the two-dimensional Euclidean space. So you would not be able to deform this or transform this path onto this. So there is no homotopy from F to G here. I hope it's okay. If you try to drag it, you have to exit the space. At this point, you are out of the space, but the transformation should happen within the space. I hope it's okay. So you can't do it outside of the space. In fact, we can, because this thing is a reparameterization, a linear reparameterization, but we can have a small result we call lemma, lemma 2. It will be 2.2, yeah, because in the last lecture we had lemma 2.1. So here, so for any path, in a space F from I to X, so therefore my notation has already pronounced that I'm talking about continuous mapping from this topological space 0, 1, but then a subset of R 0, 1. So it is given the subspace topology or relative topology into X. So therefore, for F to be continuous, even the output, the codomain here must be a space, a topological space. So therefore, it's already a topological space. For any such mapping, the composite F composed with phi, where this phi is a map, continuous map from I to I, such that, so it's a continuous map such that Phi of 0 is 0 and phi of 1 is 1. So this composite is called a reparameterization. A reparameterization of f of the map. So actually this is a definition of what we call reparameterization of f. So initially the parameter is t, and now you are changing the parameter to say s. Okay, so if you take any t, you have to change it to s, and then before you take. So it's like you are reparameterizing, like changing coordinates. Okay, changing the parameter. I hope it's okay. So like what we did before was a linear reparameterization. If you take t and change it to s, so if you put 1 minus t, t is already a time, and then you change the parameter. So, and then you have t over here. But at the end of the day, you see the function is a function of s instead of a function of t. So what you are doing is changing the parameter. So it's a reparameterization of the curve. So if you have a path, you can reparameterize in this way by choosing any such continuous mapping, 1 to 5 from I to I, and then seeing it like this. But then the theorem is that whenever you reparameterize, the reparameterization is always path homotopic to the map. Okay? Then it's called a reparameterization, and it is true that pi composed with this is path homotopic to f. Okay, so we can prove it. So we can always do that. So maybe before proving the lemma, I will prove it here, but let me just introduce this notation. If f and g are path homotopic, we shall write f is, so if I write like this, because they are functions, so they are homotopic as mappings, just not necessarily seeing them as being path homotopic relative to the endpoint. But you put a p here to emphasize path homotopic. Because without p was our notation for the last lecture, just being homotopic as path, as functions, continuous maps. But then if you want to see them to be path homotopic, because path homotopy has an extra condition that the homotopy must be relative to the endpoints. I hope it's okay. So that is why we put an extra piece. So I can say here f composed with pi is path homotopic to f. Is that okay? So what you do here is to define a homotopy. So we define a homotopy. The homotopy should be, we want to get a homotopy from this one to that one. Or, yeah. Okay. Or from F to this. So homotopy, let me call it H of T. by, so it should be a family of path into X, whatever the space is, T and I. We define it by HT of S should be equal to 1 minus T, like the linear homotopy, pi of S plus TS. Yeah. No, sorry. Not like this. So the homotopy is this. Okay, this one, H of T by H T to be equal to the composite of F with pi of T, where phi of T is a family of mappings, pi of T of S is given by 1 minus T pi of S plus TS, T times S. Yeah. Then this is a homotopy. In fact, I'm already saying it's a homotopy because I see it as a continuous family. This mapping is continuous because this is continuous. The linear mapping is continuous. Linear combination of continuous is continuous. So you have a family of continuous maps. F is already a continuous mapping, F. So the composite is continuous. So this is a family of continuous mappings. A continuous family of continuous maps. So it's a homotopy. I hope it's okay. And to see that it's a homotopy from F to where? To F composite phi. We check these two properties. First of all, H0 of S should be equal to F. Okay, and what will that be? It will be F of 0, okay, of S, the composite. But that would be equal to F of phi of 0, phi 0 of S. Is that okay? But what will this be? This will be F of, well, 1 minus 0, so it will be phi of S, and this will be 0 over there. Is that okay? And that is equal to this. So H0 is F composite phi. Are you following? And then the next one is to check H1 of S, and we expect this to be F because we want this to be a homotopy from here down to F. So that would be what? Well, F1 of S, is that okay? Which will be equal to F of phi 1 of S. I will write it up here. And that will be equal to what? So phi of, so actually you are using the definition of phi. So to be 1 minus 1, because T is 1. So this is 0, T, 1 times S. Is that okay? So that is F of S. So which means H1 is F. I hope it's okay. So this, with these two, we have that this is a homotopy from phi composite, F composite phi to F. So we have a homotopy. For it to be a path homotopy, we want to check that whether it is relative to the endpoint. So to see that it's relative to the endpoint, we check what? We check that ht, that is for all t, we want this to be the endpoint. That is f, well, the endpoint. So the image of 0 under the path. So this will be equal to what? F composite phi t of 0, but this would be f phi t of 0, but that would be f, well, phi t of 0 would be, so s is 0, so you have 0 here. And you remember the condition on phi, it is that phi of 0 is equal to 0, so you have 0 over here, plus what? Ts, ys is 0, so everything is 0 actually. And that is actually, so everything is f of 0, which is the 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 endpoint. You remember this is also, because this is phi of 0, that is what we got. Well, we got 0, but 0 is pi of 0, because pi of 0 is 0. So what I'm saying is that this is still f composite pi of 0. So therefore, we have the endpoint to coincide, and it is the same for all t. I hope it's okay. So the fourth condition is to take h1, ht of 1, and that will be f composite pi t of 1, but that will be f pi t of 1. But the way we define pi t, that is what? Well, so pi of 1 is 1, and then s is 1 over there. So actually we get f of 1. And that will still be f composite pi of 1, because pi of 1 is still 1. So this is like your initial point x0, and that is your terminal point x1, in the space. Okay? So this define a homotopy from the composite phi, from the reparameterization to the function, to the original path. So if you reparameterize a path, you always get, the reparameterization is always what? Homotopic to the original path. So what this is telling us is that when you want to show that two paths are homotopic, you can just establish that one is a reparameterization of the other. For once that happened by this lemma, it means they are homotopic. I hope that is okay. So this is what we are going to be doing most of the time. Okay then. So so with this, so we can look at this relation of being path homotopic. The relation of being path homotopic is also an equivalence relation. It will not be easy to check that it is an equivalence relation. This will be my next result, 2.3, that the relation of path homotopy is an equivalence relation. On the set or collection of all paths. Yeah. Path, having the same endpoint in a space X. So if you look at all paths, if you identify endpoint X1 and X2 in a space, and you want to now look at all paths with the initial point X0 and terminal point X1, the relation of the path being homotopic, having this endpoint is an equivalence relation. Okay? Yeah, having endpoints. Thank you. Having the same endpoint. So, proof. So, we want to show that a certain relation is an equivalence relation. We have three properties to show: reflexivity, symmetry, and transitivity. Okay? But then the property of this relation being reflexive is clear. So that the relation is reflexive is clear since the each path, every path every path F in the space is homotopic to itself. Is satisfy F is homotopic to F via the homotopy. So which homotopy? How do you see that a path is homotopic to itself? When what? So if I have a path from x0 to x1, F, and then I want to run a homotopy that will start from F and end at F after 1 hour interval. So at time t equal to 0, it should be F. And even at time t equal to 1, it should still be F. So every member of the family should be F. Okay? So via the homotopy Ft equal to F. Yeah. So you just stay there at F throughout the time interval. After 1 hour, you are still at F. I hope it's okay. So that homotopy is doing the job. It's like the homotopy that stays there at F at all time. Also, symmetry is clear since if F is path homotopic to G as path, then so if we assume this homotopy is happening, this path homotopy is happening via the homotopy Ft. So I can just then G will be path homotopic to F via which homotopy? So you see here what is happening. You have the F and you have G, and then you have a homotopy that does the job starting from F, and then after 1 hour it arrives here. So F0 is this one and F1 is here, okay, at G. And this is your homotopy. This is F half somewhere here. And now you are at G and you want to run a homotopy, so you reverse the homotopy so that your F1 is F0 and F half will still be F half, and you are going backward. F0 will now be F1. So you reverse the homotopy. So that homotopy will just be GT equal to F1 minus T. That will be the one that will reverse the process, okay, over still the time interval 0, 1. I hope it's okay. And it's clear it will still be a homotopy. I hope it's okay. So it's very easy to check. Okay? To see that the relation of path homotopy is transitive. So suppose F is path homotopic to G and G is homotopic to H, where the homotopy, two homotopies, one that takes from F to G and the other that takes from where? From G to H. Where this homotopy, so F is the homotopy that will take us from F to G, and this homotopy, call it G, again a continuous family of maps with satisfying the given conditions respectively. Okay, then we define maps, a family of maps. But right now I'm not assuming continuity. I just want to define and then prove that it's a continuous, the family is of continuous mappings. So the family of maps HT from I to X by HT of S to be equal to, so it should be F2T of S. That is if T is from 0 to half, and it should be G 2T minus 1 of S if T is from half to 1. Yeah, okay. Okay, then we have to show that this thing is a path homotopy. So what do we need to do? We have to show that each one of the HT is a continuous mapping. And that, well, first of all, we have to see that it is well defined, continuous, and that the two extra the conditions are also satisfied. Okay, that is what H of 0 should be equal to F, and H of 1 should be equal to H, and that HT of 0 should be equal to the point x0, you know, the initial point. and ht of 1 should be equal to the terminal point at all time, because this is what we are having. Chris, I'm coming. So we have this, and we have h, and over here we have some g. This is f. So these are homotopic, f and g. So there is a homotopy from f to g, and then we had a homotopy again from where? From g to h. So this homotopy here, this is gt, and this homotopy over here is what? ft. And then we are defining a new homotopy, and you can see what we did. So we make it, we double the speed, because this is happening in one time interval, and we want to transform f to h in also one period time interval, 1 hour, say. Okay, now you can see that if you follow ft, you arrive at g in 1 hour, and then from g to h in another 1 hour. So that will be done in 2 hours. So when you double the speed, okay, twice, so at time t equal to half, you are already at f1. So which is g. So you just double the speed and arrive quickly at g, and then in the remaining hour interval, you arrive at h. So this, so we separated the situation into two, and then we just run the homotopy with a double speed, and that get us from f to h. So this is what we did. Okay, but then we have to see that, so this thing, is it actually well defined? Because I can see that, so well, is it well defined? Yeah, it should be well defined because of what? The fact that I'm dealing with path sharing a common endpoint. Okay? Maybe before you are trying to ask a question, Chris.
Yes, like I've seen it. I was thinking of that family of G.
Okay. This family over here. Okay, from the interval, because this should be path. It's a family of paths. So that's why the domain should be I. Okay? So what we are saying here is, you can see that, at half, you have what? At t equal to half, this is f1. Okay? And at t equal to half here, this will be what? Yeah? G0. G0. You remember what F1 is? What is F1? It is G. And G0 is also G. Because F1 is the last thing in this homotopy, which is the G. And the G0 is the first map in this homotopy, the second homotopy, which is still G. So actually this mapping, the values are coinciding at the boundaries, at the intersection of the two splitted domain. So this is actually well defined. It's not direct, it's an elementary lemma in topology. We call it pestle lemma. I should write the lemma here so that we can just apply it. You can prove it. It should have been there already in your general topology class. So you can have the pestle lemma here. Maybe I should call it no-name. So pestle lemma. Just want to pick it from our general topology and use it over here. So I just want to say by pestle lemma, this thing is well defined and continuous. So generally speaking, you state the pestle lemma as this. If A, B are closed subset of a space, so topological space X, with the space being the union of A and B, they don't have to be disjoint. Okay? And F is a mapping from A to some other space. It doesn't have to be this same space we are talking about. G also a map from B to some that other space Y, such that with well, F restricted to the intersection is equal to G restricted to the intersection. So at the intersection, they coincide, the two functions, because A and B may intersect. Okay? So if you take this, then the space will not be enough for me. I will clean here. So then, the mapping H from X to Y given by H of X is equal to F of X for X in A and G of X for X in B is both well defined and continuous. So I should also say that this these are continuous mappings. So maybe it's a condition that must be stated there. F and G are continuous map, are continuous with this condition. So if you have two continuous mapping like this, and you define a map on the domain, you know, F and G, then it is also continuous and is well defined. Well defined in the sense that at the is clear, well definedness, because they share, if at the intersection point the values are the same. So you have the mapping to be well defined, and then it is continuous. It is called pestle lemma. It's like you are pasting this function with that function. You have the function f, and you have the function g, and you have the function g. So this is what you are doing. Okay? So you see, you pasted the functions here. So this is your h. So when you paste two functions together, the resulting function is continuous. So these mappings are continuous by pestle lemma. So this is what we have. So that's what I mean by the application of that pestle lemma. So what we have is to, so by the pestle lemma, since we have reminded ourselves of what it is, then we can quote the lemma. It's not difficult to prove. You can just do it. It's an easy exercise. So by pestle lemma, HT is both well defined and continuous for each what? For each T in the domain. So that is a family of continuous mappings, continuous family. To see that it is a homotopy from F to G, path homotopy, from F to where? To H, not to G. So we check the three conditions, the four conditions. So what are the conditions? The first condition is to check that H0 of S should be equal to F of 0. But that is f of 0, that's what we define it to be. So it's clearly f of 0. Yeah, well, it is f0 of 0, but f0 is f of 0, because f0 is the first entry in the homotopy from f to g. Is that okay? And then h1 of s should be equal to what? Yeah, at 1 you are here, so this will be g0. G0, well, g1, sorry, okay. It is g1 of s. But what is g1 of s? This is the last function in the homotopy taken from g to h. So this is actually h of 0. Okay, so this homotopy is from f to h, and it should be relative to the endpoint. So we must to check that it is independent of the endpoint. So it's independent of 0. So at all t, this is equal to what? So for all t, this will be yeah. Well, if t is in here, you will, it's actually always f2t of 0 for t in between here, or it is g2t of 0. But then each one of this is already a member of the homotopies, so it preserves the endpoint. So this is actually nothing but x0, the initial point of f and g altogether. And likewise for the other one. Okay. Likewise for the other one, ht of 1, you still get x1. I hope it's okay. So the homotopy is clearly relative to the endpoint. Okay? So this proved transitivity. And hence, that relation is an equivalence relation. So the relation of homotopy, path homotopy, is an equivalence relation in the class of all paths with the same endpoints. So this is what we have. Yeah. Okay. So with this, we I think because next we are going to define operation on path, because we can also define operation on path. We can perform like multiplying paths together. Since you know our target, this is what we do. We want to actually define an algebraic structure on the topological space, and this algebraic structure is that of a group. So we now want to use path. We are going to be working with some special classes of path. These are the ones that share the endpoint. That is where the end and the initial and the terminal point are the same, which we call loops. And then we now use them to define an operation on path. So we are going to start that discussion in the next class. I think this is a good point to stop, so that in the next class we start talking about the operation of concatenation on path, and then we now proceed into talking about loops and defining group structure on these loops. Thank you very much.